Welcome to lecture 14. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. The name of the course, Geosynthetics Engineering in Theory and Practice. This is module number 3, lecture number 14, Geosynthetics Properties and Test Methods. I now show the recap of the previous lecture, what we have covered, that is permittivity of cross plane permeability, that is under constant head permeability test and falling head permittivity test. Then transmittivity or in plane permeability, that is under full length in plane flow and radial in plane flow. And next, endurance property, that is abrasion test or abrasion resistance, ultraviolet or sunlight degradation, gradient ratio or clogging test, hydraulic conductivity ratio, HCR or clogging test. Now, we will discuss the geosynthetics clay liner, that is GCL, properties and test method. Geosynthetics clay liner consists of bentonite clay or other very low permeability material which is sandwiched between geotextile and or geomembrane. These are used as a hydraulic barrier. So, this material may be bentonite and sandwiched between the non-woven geotextile, bentonite, it may be bottom is woven geotextile and top is woven geotextile, or this is the bentonite, is bottom is non-woven geotextile and top is geomembrane, or this is bentonite, this bottom is woven geotextile and top is geomembrane. So, you can see that one of the sample like this, you can see that here is the woven geotextile material and sandwiched by this also non-woven geotextile material, and the bentonite is inside between this woven, non-woven and woven geotextile material. So, this is the kind of the geosynthetics clay liner material, and this is alternative to geomembrane material, and when this bentonite is come and contact with the water, so it will act as a barrier. So, we will show that some of the test of this geosynthetics clay liner material. So, before that going through the test procedure, we would like to focus what should be the properties of the bentonite. This is various properties of the sodium bentonite. It contains water content 7.082 percentage, liquid limit 407.53 percentage, plastic limit 37.21 percentage, plasticity index 388.73 percentage. So, there are also sodium bentonite, calcium bentonite. So, you are also to be equally careful what kind of bentonite you should require for the preparation of the geosynthetics clay liner. So, here we have developed two kind of the geosynthetics clay liner, one geosynthetic clay liner A, another geosynthetic clay liner B, and you can see this is the geosynthetic bentonite is the middle and this is the lower geotextile, this is the upper geotextile. Similarly, for this GCL B. So, two different types of the material, one is GCL A, one is GCL B. So, initially we have to calculate what will be the mass per unit area of geosynthetics clay liner as per STM D 58,993. So this is very simple way to determine that mass per unit area of geosynthetic clay liner. You can see this is the sample, this is the white color and this is the black color. This is the test sample of size 100 millimeter by 100 millimeter, and you are putting in a weight machine with an accuracy of 0.01 G, and sample are oven dried at 110 degree centigrade for 24 hours. And then initial moisture content of the clay component of geosynthetic clay liner or W clay can be estimated as follow, that is W of clay is equal to Mi by A minus mGCl by M clay into 100%, where Mi is initial mass of the geosynthetic clay liner specimen and A is area of the specimen, mGCl is the dye mass unit area of GCl, and M clay mass per unit area of dye clay component, that is gram per meter square. So from this you can calculate that what should be the initial moisture content of the clay component in a GCl. So this is the kind of the, I say that geosynthetic clay liner, and this geosynthetic clay liner is performed for the tensile strength. So what will be the tensile strength of this material? So this is wide with tensile strength have performed for the sample GCl A and GCl B as per STMD 4595. So you can see here that strain rate is 10 millimeter per minute and the width of the sample is 200 millimeter and this gauge length is about 100 millimeter. So this is geosynthetic clay liner test specimen have performed in a universal testing machine. You can see for the sample here what is the type of the failure, there is a formation of neck, and similarly for the geosynthetic clay liner B sample also failure. You can see very typical neck type of the failure as observed for both the sample GCl A and GCl B. You can see here the tensile strength versus elongation curve for the GCl A and GCl B. You can see it is increasing and then is reached to the top and then it is the decreasing. You can see elongation. Elongation is more 100% and near about let us say 130-40% elongation, and the tensile strength is very very less. So elongation is more. So this is like a geomembrane material. So another test for this bentonite is that free swelling test, STMD 5890. So these are the tests are very important when you will design for the landfill or the canal or the dam, whatever you use these geosynthetic clay as a liner or as a barrier. So this is free swelling of sodium bentonite clay. So this is a graduated cylinder is filled with 100 millimeter deionized water, and then 2 gram of the sample of dried and finally ground bentonite clay is dispersed into the cylinder in 0.1 G increment. Then a gap of minimum 10 minutes between the two successive addition is maintained to allow for full hydration and settlement of the clay at the bottom of the cylinder. Then measure the volume of the settled clay occupied by the cylinder after 24 hours. The standard certified minimum swelling index value is 24 ml per 2 gm as per STMD 5890. You can see that after the 24 hour, you can see here after the 24 hour you can measure that what this is extension here. So you can measure that it will be the 24. Okay. So that it should satisfy the minimum soiling index criteria. If it satisfies, then it is okay. If it is not satisfied, you have to be careful to think that what alternative bentonite system is to be added, or what is the repetition of the test are also needed, but that is the minimum soiling index value needed. Also Heaton etc., they also recommended that a minimum soiling index of 24 milliliter per 2 gram of bentonite. Next, fluid loss test as per STM D5891. Fluid loss is a measure of bentonite slurry's ability to form a low permeability filter cake. The test is performed in a 3-inch diameter cylinder of 2.5 inches in height. A porous stone is placed at the base of the cylinder with a thin filter paper placed over it, and together they represent the porous formation. A predetermined ratio of bentonite and water is mixed in a mixture to form solid slurry. 6% of the slurry is poured into the cylinder. The cylinder is then pressurized to 100 psi. As the water drains from the bottom of the cylinder, a filter cake forms on the filter paper, retarding the flow of filtrate. The filtrate is allowed to flow for the first 7.5 minutes of the test, and then flow is collected for the next 30 minutes. The volume collected or the total fluid lost in 30 minutes is measured and reported in milliliter or ml. A lower amount of filter collected indicates the bentonite is more effective at sealing and therefore less permeable. The reported value must be more than 18 millimeter as per the STM D5891. Now some tests also have performed for moisture absorption sets. Now sodium bentonite present in the geosynthetic clay liner can absorb water from the adjacent soil. Here you can see that water content versus the time for a geosynthetic clay liner A placed in contact with the sand at various water content. So soil with 2% water content can result that 50% of hydration of the GCl after 1 month. This you can see that this is the percentage of the soil with water, different percentage of the soil with water content. So in this curve you can see that after this 1 month, you can see here that after about a month, okay, that is reached about the 50%, here 50% hydration of GCl. Okay. The time of hydration is very rapid. Similarly, you can see the water content versus time for the sample GClB, which is placed in contact with sand at various water content. This after Daniel ETL. So this is the various water content, 2%, 5%, 10%, 18%. Here also you can see after 30 days almost it is constant. So it reached the value about the 50%, water content 50%. Now hydraulic conductivity of GCl as per IS 2720-17, it is the ability of a geosynthetic clay liner to allow the passage of liquid through it. The lesser is the hydraulic conductivity, better is the performance of GCl in field. Since GCl contain mostly bentonite clay, its hydraulic conductivity is calculated by falling head permeability test. These tests are conducted according to IS 2720. To achieve the field condition, GCl are covered with the sand having a permeability value considerably greater than the GCl so that it does not affect the permeability of the GCl. It is observed that head loss is almost constant after 20 days. Therefore, the hydraulic conductivity is calculated after 20 days. So, here the RIGI-12 permeameter setup, here the permeameter test setup for hydraulic conductivity test. So, permeability of the geosynthetic clay liner is decreased with the increase in the bentonite quantity. The needle punching of GCl did not affect its permeability too much. These small holes created by the needle punching are self-healed due to the bentonite soiling. So, this figure, it is shown the variation of hydraulic conductivity with respect to the bentonite quantity. This is the bentonite quantity, that is kg per meter square, and this is the hydraulic conductivity, and that is meter per second. So, this is for the GCl sample A and also GCl sample B. So, you can observe from this figure that hydraulic conductivity of the GCl A and the GCl B is less than 1 into 10 to the power minus 11. Here you can see 1 into 10 to the minus 11 meter per second. When the bentonite quality is greater than 5.5 kg per centimeter square, generally the hydraulic conductivity of compacted clay liner is in the range of 10 to the power minus 9 meter per second. So, what we wanted to conclude here, that when you use this compacted clay liner, you know that what is hydraulic conductivity of the compacted clay liner, and that value may be 10 to the power minus 9 meter per second. But alternative to the compacted clay liner, if we use the geosynthetic clay liner whose coefficient of permeability or the hydraulic conductivity is about 1 into 10 to the power minus 11 meter per second. And also at the same time we should know that what quantity of the bentonite is required. So, it has been observed sometimes if this bentonite quantity is greater than 5.5 kg per meter square. So, you will obtain the better hydraulic conductivity of the geosynthetic clay liner. So, here showing in the table that hydraulic conductivity of GCl with different amount of bentonite. So, bentonite mass per unit area, you can see kg per meter square, that is we have been given 3.5, 4.5, 5, 5.5, and this hydraulic conductivity for GCl A, that is meter per second, when the mass is 3.5 kg, this hydraulic conductivity 4.5 into 10 to the power minus 8, and hydraulic conductivity for GCl B, that is meter per second, 6.7 into 10 to the power minus 9. When the bentonite mass per unit area 4.5 kg per meter square, the hydraulic conductivity for GCl A is 7.1 into 10 to the power minus 10 meter per second, and for the GCl B 3.1 into 10 to the power minus 10. When the bentonite mass per unit area 5, then hydraulic conductivity for GCl A 2.6 10 to the power minus 10 meter per second, and the hydraulic conductivity for GCl B 7.4 into 10 to the power minus 11. Then when the bentonite mass per unit area 5.5, then hydraulic conductivity is 5.5 into 10 to the power minus 11, and for the GCl B 4.2 into 10 to the power minus 11. You can see that how you are having better result with increasing the mass of the bentonite or bentonite mass per unit area. So, you can you can fabricate it or develop a geosynthetic clay liner where you require the bentonite, and this bentonite, sodium bentonite, is abundantly available in India. So, it can be manufactured at this GCL, which will be the more convenient to produce this kind of the product, and it is alternative to the geomembrane material. Production of geomembrane material may be the costly, but as the both the oven and non-oven geotextile materials also are available, and the bentonite is abundantly available. So, this kind of the product would be very useful for different project in India, like this landfill project or whatever, in any project where you require for the proper kind of the barrier or to control the seepage. In this slide, I am showing that one canal or the reservoir, and this is the compacted clay liner, and alternative to the compacted clay liner, now we place in this canal one geosynthetic clay liner. This is geosynthetic clay liner. Okay. So, you can see that how the water can flow in case of the compacted clay liner. You can also observe how the water can flow through the geosynthetic clay liner. I said when this water will come and contact with the geosynthetic clay liner, and it is soil, and it will act as a barrier. It will act as a barrier. So, I am giving one example. So, here you can see height of the canal of reservoir is 5 meter, and thickness of the compacted clay liner is 600 millimeter. So, you can see that this is 600 millimeter, height is 5 meter, and this is 600 millimeter. Whereas, in case of the GCL or geosynthetic clay liner, the TG is 6 millimeter. So, you can see this TG will be the 6 millimeter, and coefficient of permeability of clay liner 1 into 10 to the power minus 8 meter per second, and hydraulic conductivity of geosynthetic clay liner is 3 into 10 to the power minus 10 meter per second. Now, in this example, that the solution is here for compacted clay liner. So, hydraulic gradient I is equal to H plus Tc divided by Tc, and whereas that thickness of the compacted clay liner is 600 millimeter. So, this is H is the height of the canal, that is 5 meter. So, this is to be converted into meter. So, that is why this will be the Tc will be the 0.6, and this height is equal to the 5. So, I is equal to 5 plus 0.6 divided by Tc is 0.6. So, this hydraulic gradient I will be 9.33. Now, quantity of Q of CCl, quantity of flow of water through the compacted clay liner, that you know from the Darcy's equation, that QCCl is equal to Kc into H plus Tc divided by Tc into A. So, Kc is given is 1 into 10 to the power minus 8 meter per second into H plus Tc. H is the 5, T is 0.6 divided by Tc is 0.6 into A 1 is to 1. So, you will have this Q CCl is 9.33 into 10 to the power minus 8 meter cube per second. This is the quantity of water flow through the compacted clay liner. Now, alternative to the compacted clay liner, if you can adopt the geosynthetic clay liner, which thickness Tg is given 6 millimeter, Tg is equal to 6 millimeter, and the hydraulic conductivity of the geosynthetic clay liner is 3 into 10 to the power minus 10 meter per second. So, here the QGCL will be equal to 3 into 10 to the power minus 10, that is here, KGCl 3 into 10 to the power minus 10 into H plus Tc, that means 5 is the reservoir height, plus thickness you can see less of GCl, that is 6 millimeter. So this is 0.006 millimeter divided by Tc, that means 0.006 into 1 into 1. So this will give you the 25 into 10 to the power minus 8 meter cube per second. Now if we take the ratio of QCl by ratio of QGCl by QCl, you can have this QGCl is 2.5 10 to the power minus 8 divided by QCCl is 9.33 into 10 to the power minus 8. So this is 2.6 approximately 3. So flow through geosynthetic clay liner is 3 times higher than the compacted clay liner. Next, the X-ray diffraction test. X-ray diffraction is a versatile non-destructive technique that reveals detailed information about the chemical composition and crystallographic structure of bentonite. So XRD test was performed in metallurgy department of IIT Bombay. This test is performed to know the complete mineralogical structure of sodium bentonite. The test is based on Bragg's law. So what is Bragg's law is 2D sin t is equal to n lambda, where d is lattice inner planar spacing of the crystal, theta is equal to X-ray incidency angle is Bragg's angle, and lambda is wavelength of the characteristics X-ray, and in order of diffraction. By varying the angle, the Bragg's law condition are satisfied for different d spacing in polycrystalline material. Plotting the angular position and intensities of the resultant diffracted peaks of radiation produces a pattern which is characteristic of the sample. The XRD test machine is available at IIT Bombay. You can see this is the X-ray diffraction test facility, and this is the variation observation from the test. This is between the spacing and the position to theta, how this spacing is decreasing and position to theta is also increasing. So this figure shows the various result of X-ray diffraction test between the relative intensity, that is in percentage, to the positioning of 2 theta, and this figure shows that what will be the height and this with the position of 2 theta. So from this, the complete description of sodium bentonite is determined by using JCPDS, or called Joint Committee on Powder Diffraction Standard software. From this figure, okay, this is suppose B and also the C. So for 100% relative intensity, the value of 2 theta is determined, which is 31.2 degree. Corresponding to this 2 theta value, the spacing is found to be 2.376 Armstrong from the figure. So he can also determine from this figure. And now the analysis is done in JCPDS in a spacing range of 2.375 Armstrongs, that is lower limit, to 2.377 Armstrong for the upper limit. The main mineral component of bentonite is found to be montmorillonite, that is about 69.89%. The chemical present in this bentonite are shown. You can see that what will be the percentage of chemical present in the sodium bentonite. This mineral is silicon dioxide is about 69.89%, aluminum oxide is 14.66%, magnesium oxide is 4.02%, sodium oxide is 2.64%, calcium oxide is 2.05%. Shear strength of the geosynthetics clay liner. Bentonite has very low shear strength after hydration. So, the unreinforced geosynthetic clay liner show very low shear strength. For higher shear strength application, reinforced geosynthetic clay liner are required, in which the carrier geotextile are connected by the needle punched fiber that transmit the shear stresses across the bentonite layer. For the stability analysis, the internal shear strength and the interface shear strength is evaluated through direct shear box test. The internal shear strength represent the shear strength between the geotextile and the bentonite layer, while the external shear strength represent the shear strength between the GCl and adjacent material, that is sand and geosynthetics. All the test was carried out in a direct shear box of cross section area 60 millimeter by 60 millimeter. Now, internal shear strength of the GCl. Internal shear strength of the GCl is determined with direct shear box test. All the tests are carried out according to the IS 13326 part 1 1992, reaffiliated in 2002. The strain rate in all cases was 1 millimeter per minute. Normal stresses range from 50 to 150 kilopascal. The test was performed in two different states, dry condition and hydrated condition, that is free soil. An acrylic block is used to hold the GCLs at proper position. For avoiding the movement of the GCL during the testing, GCL is glued to the acrylic block using adhesive. This you can see that figure. This is the geosynthetic clay liner sample is attached with the acrylic block, and this is the direct shear test machine. So, here perform the shear test versus this horizontal displacement. The various results for both the dry and the wet condition for the geosynthetic clay liner A and geosynthetic clay liner B has been performed under the pressure of 50 kilopascal, 100 kilopascal and 150 kilopascal. You can see here how the shear stress is increasing with the increasing of the hydraulic displacement, but you can see that when hydraulic displacement is about 2 millimeter, and you can see you can have almost that maximum stress value, and then it is gradually decreasing, and almost later on it is as a constant. So, similarly for the geosynthetic clay liner A in wet condition, this is the shear stress versus the horizontal displacement. You can see here also similar nature of the curve you can obtain under the different pressure 50, 100 and 150 kilopascal. This figure shows the shear stress versus the horizontal displacement for the GCLB in dry condition. You can see that how the shear stress value is increasing. It goes up to 120 and then it is decreasing and then almost like a constant. All the curve under the various pressure nature is the same, and the horizontal displacement is relatively less, whereas the shear stress is more. But this is the figure for the geosynthetic clay liner B sample in wet condition, and this is the relationship between the horizontal displacement and the shear stress under different pressure, you can see that the shear stress is increasing and then it is decreasing almost like a constant, but from here it can be some conclude that when the GCL is in the dry condition, the shear stress value is higher, and when the GCL is in the wet condition, shear stress value is relatively low. And but almost the horizontal displacement is the same whether it is a wet or it is a dry condition. So, this is a kind of the behavior of the geosynthetic clay liner. Now, this figure shows the peak failure envelope for the geosynthetic clay liner A and this B, both with the dry and as well as the wet condition. So, this peak failure envelope, all these cases are shown here. This is the relationship between the shear stress versus the horizontal displacement. You can see that shear stress is increasing with the increase of the horizontal displacement. Whether it is a dry or wet, that failure envelope is almost the same in nature. So, here detailed result of the direct shear burst test are tabulated in this figure. You can see sample condition, whether it is a dry or the wet, or the adhesion value is 13.8, this is 9 point, weight is 9.81, friction angle delta is 32.77, and for wet condition 15.01, horizontal displacement in dry condition 1.8 to 2.4 millimeter, and wet condition 2.1 to 3.3 millimeter, and this is R square is 0.9948 and 0.9967. You can see that when it is the dry condition, this adhesion and the friction angle is more compared to when it is the wet condition, and horizontal displacement is not so much significant difference whether the sample is in dry condition as well as the wet condition. Now, this is for the geosynthetic clay liner B. You can see whether it is a dry condition and wet condition, this adhesion factor 15.88 kilopascal for dry, this is 14.87 kilopascal for wet, this is 35.407 this friction angle for dry, and wet is 18.53. Then horizontal displacement for dry 3.3 to 3.6, and this wet is 2.4.3. So, in all cases, whether the geosynthetic clay liner is the dry condition or the wet condition, most of the cases the adhesion value is higher with respect to the wet condition. Both the adhesion and the friction angle is higher, but the horizontal peak displacement not so significant different. So, what summary of the GCL A and GCL B property can be conclude? The various physical, mechanical and the hydraulic property of GCL A and GCL B are shown, and where Ca is the adhesion between the bentonite and the geotextile of GCL, and delta is the interface friction angle between the bentonite and the geosynthetic clay liner. You can see here test properties of GCL A and GCL B. This is the bentonite, sodium bentonite. This is the what kind of bentonite quantity you have taken. This is 5.5 kg per meter square. This is also 5.5 kg per meter square. This is upper carrier geotextile, that is needle punch non-woven geotextile material. This also needle punch non-woven geotextile material. This is lower carrier geotextile, needle punch non-woven geotextile material, needle punch non-woven geotextile material, but mass per unit area for GCL A is 248 gram per meter square and GCL B is 206 gram per meter square. Mass per unit area of GCL, geosynthetic clay liner, is 5.62 kg per meter square, and for GCL B is 5.58 kg per meter square. Thickness is 10.6 millimeter. This is for GCL B 7.2 millimeter. Moisture content 12.2%, and for GCL B 11.66%. Tensile strength of GCL is 16.56 kilonewton per meter. and for GCLB 20.01 kilonewton per meter. Elongation as peak load is 143.8% and for the GCLB is 100%. Hydraulic conductivity 5.5 into 10 to the minus 11 meter per second for GCLA and 4.2 into 10 to the minus 11 meter per second for GCLB. Shear strength value in dye, Ca is 13.8 kilopascal, delta is 32.77 degree, and this for and the shear strength, this in the wet condition Ca is 9.8 kilopascal and delta is 15.01, and for GCLB the Ca is 15.88 kilopascal, delta is 35.40 degree, and Ca is 14.87 kilopascal and delta is 18.53. This is all the information is given by confirming this test. Now, geosynthetic clay liner as a composite liner, the waste generated leachate that flow gravitationally downward into the groundwater. Therefore, it is needed to provide a suitable barrier layer or the system. GCL can be used to reduce the leakage rate. The basic concept and the placement of the GCL are shown in this figure. You can see if this is the leachate formation in the landfill, there is a formation of the leachate. So, leachate can flow if we provide with a compacted clay liner, that is the traditional method, and you can see how the leachate can flow, even then it is a compacted clay liner. Now, in case of the compacted clay liner, you can see if there is a hole, let us say it is a geomembrane material, and leaches you can pass through this also and can flow. So, how the leachate flow here? So, this is the geosynthetic clay liner, or it may be the geomembrane, but what should be the concept and the placement of the GCL, what will be the concept and the placement of the geosynthetic clay liner. So, this is we are providing here the geosynthetic clay liner, and you can see here is the bentonite and the geotextile on the top and the bottom. This is like a sandwich, but when the leachate passed through this, then you can see the direction of the flow, leachate flow, this direction. Whereas, when the leachate flush in clay liner is vertically downward, okay, but here you can see it passes like this, like a transmittivity, like this, it flow like this. So, in case of the geosynthetic clay liner, liquid cannot be penetrated into the clay liner because of the transmittivity of the geotextile. The liquid can flow along the plane of the geotextile. Giroud and Bonaparte 1989 developed the equation as flow in case of GCL with geomembrane for rectangular slit in a geomembrane with slit length greater enough than width. Then he gave this equation, Q is equal to pi K GCL, that is permeability of the GCL meter per second. This is HW, that is total head loss in millimeter, and this is the T is the thickness of the GCL in millimeter, and this divided by ln 2T divided by B, where B is the width of the shield in the geomembrane in millimeter. And in case of GCL with geomembrane for circular hole in the geomembrane, if it is a circular hole, so then Q will be equal to pi into K GCT, then HW plus T into D divided by 1 minus 0.5 D by T, what D is the hole diameter. So, this is a circular hole, but in this case this is the width of the shield plane B, and if it is a circular hole, this is the difference between the circular and width of the hole of the geomembrane. Now, I am giving one typical example where K of GCL is equal to 6 into 10 to the power minus 11 meter per second, HW is 350 millimeter, B is 1.5 millimeter and T is 5 millimeter. Now this is the equation Q, you know. Now if you substitute this value, then Q will be equal to pi into this is K, GCL is 6 into 10 to the power minus 11 into HW, HW is 0.350 in meter, and then this is the T, T is 5 meter, that means plus 0.005, this divided by ln into 2 into T, 2 into that is the T, that is 0.010, this divided by this is the 2 of T, that means 2 into 5, that means 10, that is 0.010, this divided by B, B is equal to this 1.5 millimeter or 0.0015. So if you calculate, you can have this, you can have 3.52 into 10 to the power minus 11 meter cube per second. Now in example 2, in the same problem as in example 1 we discussed, what the diameter D is 1.5 millimeter, then you calculate the discharge. So it is a circular hole in the geomembrane, then equation is changing, this is the equation. So in the same formula, if you calculate the what is Q, this everything is same, only that it is the D value will change. So D will be the 1.5 millimeter. So you substitute this value, that is 0.0015, and also this will be the 0.0015. Other remain constant. So if you substitute this value, you can see that Q value will be equal to 0.0118 into 10 to the power minus 11 meter cube per second. It depends upon what will be the type of the hole pattern, whether it is a circular like the hole or it is a with wide that hole. Then accordingly you can calculate what will be the quantity of flow of leachate can pass through the GCL with geomembrane setup. Now this is some tensile strength of nanomaterial. A nanoetic is added to the polypropylene to increase the tensile strength of polypropylene. The polypropylene sample collected from the product application and research center of Reliance Industry Chembur, Mumbai. This you can see, this is the sample is been collected, this is a polypropylene grain and this obtained in raw form, and this is the source for PRCRIL India. You can see this is the bits. So this sample was prepared using the procedure as per STM D638. The mixing is done by heating the polypropylene to its melting point. It causes breaking of bond between its plate structure which exists in its natural form. Once the melting is complete, the nanothallic form cross the linkage within the sample, enhancing the strength of the sample. A suitable amount of the sample was placed in the oven for overnight, heating at a temperature of 105 degrees centigrade. The polypropylene was then molded as per the STM type V sample for tensile strength testing using a microcomputer that as shown in this figure. So this is the DSM twin screw microcomputer. This is the source from the central facility of the Department of Metallurgy and Material Science. This microcomputer was run at 150 RPM for the preparation of neat polypropylene sample at a temperature of 230 degrees centigrade. In the injection mold, cylindrical temperature was kept at 240 degrees centigrade, while the mold temperature was kept at 50 degrees centigrade. The sample were allowed in injection molding unit for molding and cooling for approximately 2 minutes. So this you can see, this is the injection mold for the preparation of STM type V sample, and this is also central facility for Department of Metallurgy and Material Science, IIT Bombay, and from this we can prepare this kind of the sample and we can perform the test. This is the dimension of the sample as per STM D638. So you know all this dimension of this sample, and then this also sample has been performed, and you can see that this is the W means here, W is the here whose length is equal to 3.18, and then some tolerance in plus minus 5 millimeter. Length is 9.53. This is length is this is length is 9.53 plus minus 0.5, and the width overall is 9.53, that is W of O. This is about 9.53 millimeter, and LO is the length overall is 63.5, length overall is 63.5, and then the G is the gauge length is 7.62. This is the G is the gauge length is 7.62, and the D is the distance between the grip 25.4 millimeter, that is D is equal to distance 24.5 millimeter, and R is the radius of fillet 12.7. This is R 12.7, and the T is the thickness of the sample. T is the thickness of the sample here, that is about 3.2 millimeter, and some tolerances is there. So this is the sample, and this prepares the sample is shown in this figure. So this is the prepared sample for market for testing for the tensile strain. So this is the universal testing machine, and this test has been conducted, and you can see that how the failure of the sample along the gauge length. The ultimate tensile strain machine is shown. The failure of sample also along the gauge length is shown. So this is the figure shows the stress strain curve of the sample. You can see that how the stress is increasing with the strain, and then it is increasing, then almost constant, and then decreasing, then again also it is increasing. So this is the additional of nanometric caused the improvement in the tensile strain up to 3.6% approximately. The mechanical property of the testing is given for the different sample 1 to 5 and tensile modulus, ultimate strain and ultimate strain, and tensile strength also has been determined. You can see that this is the tensile modulus 1.1008, ultimate strength is 38.73 MPa, and the ultimate strain is 5.796 millimeter per minute, and tensile strength is 34.22 megapascal. So like this for the other sample also it has been given in the table. So this is the one junction strength of the geocell material, which we have also discussed earlier. So how to connect the geocell material. Now ultimate versus the allowable geosynthetic property. The laboratory test versus cannot be used directly in the design. It is preferable to use the suitable modified value for in situ condition. Most cases performance tests are not possible and feasible. So the reduction factors should be considered for site specific design, as Koehner mentioned in 2005. And so far whatever we have performed the test, that is the strength related problem and also the flow related problem. So I will just show very few slides with the strength related problem, how we can calculate the T allowable value. So T allowable value will be equal to T ultimate value divided by all these reduction factor. This is reduction factor. RFC, RFID, RFCD, RBD, RFJNT, RFJCT. So these factors have to be considered for the design. So what the T is the ultimate tensile strength, then T allowable tensile strength, RFCR reduction factor for the creep, this is reduction factor for the creep, then RFID reduction factor for installation damage, then RFCD is the reduction factor for chemical degradation, and then RFBD reduction for the biological degradation, and this is RFJNT reduction factor for the joint, and this is reduction factor for the joint, and RFJC reduction factor also for the joint. So these factor is to be taken into consideration. For the different types of the application, this reduction factor is different. So you have to calculate for the design what will be the allowable tensile strength of the geosynthetics material. So you know from the test what will be the ultimate tensile strength value. If you know that, and different types of application, different reduction factor. So you have to consider that reduction factor, and then you have to determine the what will be the allowable tensile strength of the geosynthetic material. And this kind of the strength related problem you can apply for the unpaved road, retaining wall, embankment, bearing capacity, slope stabilization, rail load, pavement overlay, pavement road, roadway, foundation, concrete overlay, bridge piles for field placement, and flow related problem. The other is the flow related problem, hydraulic related problem, where psi allowable is equal to psi ultimate by 1 by this is our SBC, that is reduction factor for the soil clogging and blinding, and this is RFCR, that is reduction factor for creep of the void. This is RFIN, this is reduction factor for intrusion into the void. This is RFCC, that is reduction factor for chemical clogging, and this is RFBC, that is reduction factor for biological clogging. So all this factor is given by the coordinate for the different application, and here the application area for flow related problem is retaining wall filter, because this is all hydraulic related problem, flow related problem, erosion control filter, landfill filter, under drain filter, gravity and pressure drainage, embankment protection, coastal, lake, river and stream, ditch anchoring, and filter below fabric form. Also beneath the gabion, high embankment, seal fences and screen, culvert outlet, vertical drain, trench drain, base course drain, toe drain in dam, and pipe wrapping. With this I ended up this lecture today. Please let us hear from you any question. Thanks.